Hello everyone, welcome to the fifth lecture on the topic of optics and lasers. Today we are going to talk about the different types of lasers. So based on the active medium within a laser, there are different types. So they are usually classified either into solid state or semiconductor or gaseous lasers. So we are going to talk about a solid state laser, which will be a ruby laser. So ruby laser is the first successful laser developed, and it was in the year 1960 by Theodore Maiman. So let's see the construction of the ruby laser. So here we see a ruby laser rod. So this is actually a glass tube within which, or a laser rod, a rod in which within which we have ruby crystal, and the ruby crystal is usually given as Al2O3, and it is being doped with chromium 3 plus ions. So you have it here at the center. So that's what is going to act as the active medium. Next, we also need the resonant cavity or the resonator. So resonator is made up of mirrors. So you have mirrors on both the ends of the rods. Reflecting mirrors are given. Now, along with that, we also need a system for pumping so as to achieve population inversion and then get the stimulated emission. So for that purpose, there is an electronic flash lamp which is filled with xenon. So this is a flash lamp, and the flash lamp surrounds the ruby laser rod. Now this flash lamp is able to produce white flash of wavelength 550 millimeter. And this flash lamp, xenon flash lamp, the white light which is being produced is what is going to act as the pumping system. Now there is also a coolant used around the ruby rod in order to cool the entire system. So let's see how it works. So when we switch on the flash lamp with this power supply here, it produces the light. It produces an intense light of wavelength 550 millimeter, and that light is going to fall on the ruby. It's going to fall on the ruby. Now since it is white flashlight, there will be different components of color. So we know that white light is made up of actually a mix of the Vibgyor. So there will be different colors. So what is going to happen is the white flashlight from xenon flash lamp is going to fall on the ruby crystals, which is doped with chromium 3 plus ions. So the chromium 3 plus ions, which are in their ground state, they will absorb the green and the blue colors of the light. The green and the blue wavelength get absorbed by the chromium 3 plus ions, which are in the ground state. So what is going to happen is once they absorb that light, that white light, the blue and the green portions, the chromium 3 plus ions, they get excited to a higher state, higher energy level. They get excited. So this green arrow corresponds to the chromium ions which absorbed the green light coming from the white flash, and the blue line corresponds to the ions which absorb the blue portion. So whichever absorb the green light, they reach this particular high energy level. Whichever absorb the blue reach this particular high energy level. Now let's denote it as E3 and E3 prime. This is E3 and this is E3 prime. And the lower one is E3 and the upper one is E3 prime. These are the two high energy states. And we know that at high energy states, the ion will have a very short lifetime, that is of the order of nanoseconds. So what will happen is the ions, the excited ions, once they reach here, they undergo non-radiative transition and come towards a metastable state, which I am going to call as level E2. So the ions, the chromium ions from both E3 and E3 prime, both the eye levels corresponding to the absorption from the green light or the blue light, they will come down to the metastable state. And metastable state, we know that the ions can stay there for a longer time. Now, so this keeps on happening, the excited ion keeps on coming down towards the metastable state, and when more than half of the chromium ions population get accumulated here at the metastable state, population inversion will occur between the metastable state and the ground state. That means the number of ions at the metastable state will become higher than that what is in the ground state. So we get the population inversion. So once population inversion is achieved, stimulated emission can take place. So the next step is a random photon will be emitted by a chromium ion, and that is going to initiate a chain of stimulated emissions. So stimulated emission, as we already discussed in the previous lecture, it is occurring when a random or a chance photon initiates the stimulated emission. So we get many number of photons coming from the metastable state. So these are the stimulated emissions, and these can even undergo multiplication. And when stimulated emission takes place, obviously some of the chromium ions come down to the ground state, and during that time the energy being released will have a wavelength of 694.3 nanometer, which actually corresponds to the red light. So the resultant light coming is actually, or the photons are actually of the red light. Now what happens once we have the photons generated from the stimulated emission? All those photons will be reflected back between the mirrors on both the ends of the rod, that is the optical resonant cavity, the resonator. So multiple reflections will happen, and in this particular mirror where there is a silver mirror coating, through this the final laser, which is now amplified because of this multiple reflection between the mirrors, that will come out. So next we are going to understand a gaseous laser, a gas laser, which is a helium neon laser. That means a mixture of helium and neon. So this is the first gas laser which was invented in 1961. So here we don't have a flash lamp. So the previous it was a flash lamp. So if you guys remember, there were actually three methods of the active medium being excited to a high energy level. So one is making use of an optical light, next was electrical discharge, and the other one was a direct conversion. So the optical light was actually from this flash lamp, the white light which it was produced in the ruby laser. But now we are going to talk about an electrical discharge. So here we have a long cylindrical discharge tube, and the tube is made up of fused quartz, and within the tube you have the helium and neon gases filled with a ratio of 10:1. So that is, helium is 10 and neon will be 1. So there are two electrodes connected to the two ends of the discharge tube. There is a positive and negative electrode. So now here we can see that even though there is a higher concentration of helium, it is actually the neon atoms which are going to behave as the active centers, and the helium atoms are only going to help in the excitation of the neon atoms. Now one more point is the distance between the mirrors here. So we have the resonant cavity, the resonator, optical resonator. We do have mirrors here. So the distance between these two mirrors will be n lambda by 2. It will be an integral multiple of lambda by 2, where lambda is the wavelength of the light being produced. This is done so that it produces a standing wave pattern. So you all know about what is a standing wave or a stationary wave. So the mirrors, actually there is a fully silvered mirror on one side and partially silvered mirror on the other side, And obviously, wherever there is a partial coating, that is where the output is going to come out. We will talk about the Brewster windows later. So now what is going to happen is when you switch on this DC power supply, the electrodes are going to produce the discharge. There is an electrical discharge which is going to happen, and that will ionize the gaseous atoms of helium and neon. So in another sense, I can say the electrons are being accelerated between the electrons through both the electrodes through the gaseous mixture. So when ionization occurs, we obviously say that it produces more electrons. So the entire current which is being given near the power supply is going to produce lots of electrons which are going to be accelerated between both the electrodes. Now these electrons transfer some of their energy to the helium atoms in the gas. So how is the excitation actually going to start? So from the energetic electrons produced due to the discharge, the helium atoms will get energy. They absorb that energy from those electrons. So the electrons which are belonging to the helium atoms at the low energy level of the helium atoms, they will gain energy from the due to the discharge, and then they get excited towards the excited state. They get transferred towards an excited state, or they go towards their metastable state. So in this case, it actually is going towards two metastable states given by 2,1s and 2,3s. So now we know that metastable states will have a longer lifetime. So the resultant is you will get more number of helium atoms moving towards these metastable states. So more number of helium atoms can reach over this both these metastable states. So you will get more number of helium atoms in the metastable state than what is there in the ground state. Now the next what is going to happen is we do have some neon atoms already there in the ground state. So the helium atoms which are now there in the metastable state here, they are going to collide with the neon atoms in the ground state. A very important point to be noticed. Helium atoms in metastable state will collide with neon atoms in the ground state. So in this collision, we know that helium atoms are at a high energy level here and the neon atoms were at low energy level. So because of the collision, the energy gets transferred from the helium atoms to the neon atoms. So neon atoms gain energy and they go towards their high energy level and actually reach their excited energy level given by 3s and 2s. Two energy levels, 3s and 2s. So in principle, we can say that the helium atoms which were in the metastable state have helped the neon atoms to go towards the excited state. Now, this kind of energy transfer between the helium atoms and the neon atoms is actually you can say that it is a resonance energy transfer. Now the next step is we have the neon atoms here at the excited states. So what they will do is they undergo transition to the metastable state 3p and 2p. So there are three ways in which it can go. So 3s, from the level 3s to 3p, they can undergo a transition and release photons of wavelength 3.39 micrometer, which falls in the infrared region. From 2s to 2p also the transition can happen and produce photons of wavelength 1.15 micrometer. And from 3s to 2p also the transition can happen and produce light of 632.8 nanometer, which again will be of red color. So actually the 3s and 2s levels were metastable state, and even 3p and 2p are the metastable states of neon. So I'll just repeat whatever we discussed now. So we had the helium atoms initially in the ground state. They absorb the energy due to the from the electrons produced due to the electrode discharge, and energy get the helium atoms absorb the energy, go towards their metastable states of 2s, 3s and 1s, these two states, and they can stay there for a long time. So this will help them to collide with the neon atoms which are there in the ground state. So resultant is some energy transfer between helium and neon atoms gain energy from the helium atoms and go towards their excited state, which actually is a metastable state. So they reach to through either 2s metastable or 3s metastable states. Now from 3s they can jump towards 3p or 2p, and from 2s they can go towards 2p. So all these transition between the S and P level in neon can result into infrared emission or else an optical emission of 632.8 nanometer. Now the next step is that they can, once here in the 3p and 2p level, they can undergo fast radiative transition to the 1s level. So this will be a spontaneous transition. This will be a very fast, very quick, spontaneous emission. So in another sense, we can say in a spontaneous emission, we do get some photons being produced. So these photons which are now produced, what they can do is they can be absorbed by the 1s atoms. So from 2p level, the neon atoms come towards the 1s level by means of quick spontaneous emission of photons, and those new photons can trigger the excitation of new atoms from neon atoms from this level 1s. So what can happen is the 1s atoms can get again excited towards the higher energy level. So they can go back to the 2p or 3p level. So this basically what results in increase in number of atoms in 3p and 2p level. So you will get more number of atoms here than what was there in the 3s and 2s level. So that is against population inversion. So let me just repeat what we discussed just now. So we had the stimulated emission happening between the 3s, 3p and the 2p, 2s, 2p levels, resulting in either infrared or red light or optical light. And what we said is the atoms, once they have reached the p levels, the 3p and 2p levels, they can do spontaneous emission of photons and come down to the 1s level. So due to the spontaneous emission of photons, those photons can actually trigger the 1s atoms to go back to the 2p and 3p level. So this will result in increase of atoms in the 3p and 2p level in comparison to the 3s and 2s levels. So that will affect the population inversion. Population inversion and stimulated emission is actually happening only when the 3s and 2s level have more atoms than the 3p and 2p levels. But if 3p and 2p get more number of atoms, then population inversion will be affected or population inversion stops. Now, the atoms in 1s level can now come down to the ground state by means of colliding with the walls and undergoing diffusion. So they collide with the walls of the discharge tube. This discharge tube here, the atoms can collide with the walls of the discharge tube here and lose some energy and come down to the ground level. So one important point to be noticed is that suppose you have a larger diameter of the discharge tube, then the gain of the helium neon laser will be less. The output of the helium neon laser will be less. Or we can say that the gain of the output of the helium neon laser is inversely proportional to the diameter of the discharge tube. So because of that reason, discharge tubes are usually made of smaller size or having a few millimeter of diameter, so that we get maximum output from the helium neon laser. Now, so we once we have all these light coming out due to the stimulated emission, the next step we know is to get reflected between both the mirrors. So the stimulated photons will undergo multiple reflection between the fully silvered and partially silvered mirrors. So in the previous lecture on optical resonant cavity, we did say that sometimes there is a loss of light. So we are having Brewster windows here, which is going to help in such a way that there is no loss of light. So whatever photons are being produced here due to stimulated emission, all of them are getting reflected back and forth, and the Brewster windows make sure that there is no loss of light when the multiple reflection takes place. And finally, the output, what is coming out will be a polarized beam of laser. So that's the working about helium neon laser. So until now in this lecture, we discussed about two different types of lasers. That is a solid state laser, which is a Ruby laser, and a gaseous laser, which we considered as a helium neon laser. Now let's just discuss some applications of laser. So first one is for communication, and the simplest example is optical fiber communication in order to transmit audio, video signals and data for long distances without any kind of loss or deviation. So any kind of without any attenuation or distortion. Now another one is that we understood this property of directionality of the laser beam. That means it doesn't have a wide spread. So it's a very narrow angular spread which the laser beam has. Because of that, it can be used for communication between Earth and Moon, or else with the satellites and Earth. Now another thing, laser radiation will not be absorbed by water. So they can be used in underwater communication networks. Now let's list out the industrial application. Basically it's used for metal cutting, welding, hole drilling, etc. And also for heat treatment in automobile industry. And then in electronic industry it is used for trimming the components of integrated circuits. Major applications come in medical, in eye surgery, and then skin related treatments like plastic surgery or any injuries or anything with respect to the skin surface or the skin tissue. Now further we can see that laser is used for destroying kidney stones and gallbladder stones, and then in cancer diagnosis and therapy to control any hemorrhage. And we have endoscopy process also being done by laser to detect some hidden parts within the body. Now computers, you will be aware of laser printers. Then we also can use lasers so that large amount of data can be stored in the CD-ROM, or which can result into storage, increasing the storage capacity of the CD-ROMs. Next, thermonuclear fusion, so that it helps in nuclear fusion reaction, because in nuclear fission reaction we need very high temperature and pressure. This can be done by having a concentrated amount of energy, laser energy, in a very small volume. So that will help for increasing the temperature and pressure, and then ignite the nuclear fusion reaction. Then more into scientific research for studying the nature of chemical bonds, then for speeding up the chemical reaction processes. Then let me list some of a very few of these. So there are so many actually. And then to estimate the size and shape of cells, air pollution to find the size of dust particles. Holography is a very important application. And then we can, yes, coming to forensic science, we have lasers being used to develop hidden fingerprints. So the ones, obviously, if you look into different textbooks or just Google it up, you will find lots of applications of laser. So thank you for watching the lecture series on optics and lasers. If you have any queries, please do leave it in the comments. I'll be happy to reply you back. Thank you.